Welcome everyone. It's very exciting for us to welcome you to our first durability webinar in what will be a series of webinars that we're hoping to roll out next year, and obviously starting now. So look, I'll give you a quick intro to BCRC to start with. So look, for those who don't know, you probably all do know, but we're construction materials and durability consultants. And we like to think that we're thought leaders in this space when it comes to durability of buildings and infrastructure. We are led by our three well-known directors, Frank Papworth, Bob Munn and Martin Maraziki, who are well supported by a growing team of highly capable engineers who are some of whom are starting to make a name for themselves in their own right in the industry. We have offices all around the country in Brisbane, Newcastle, Sydney, Melbourne and Perth, from which we service not only Australia but also the Asia Pacific region. So that's just a very quick intro. Without further ado, I will move on to handing over to the first speaker today, who will be Inam Khan, our Queensland manager, who's going to talk on thermal and early age crack width modelling of large concrete elements. After Inam's talk, we will do some Q&A for Inam's presentation before we then move on to talk 2 from Martin Maraziki, who's going to talk on premature deterioration of basement structures. So without further ado, I will hand over to Inam, and please just make sure that if you have a question, you use the Q&A function at any time throughout the webinar today.
Hello everyone, good afternoon. Thank you so much for attending this webinar. So I'm going to present today on thermal and early age crack modeling of mass concrete elements. Now to go into thermal and early age crack modeling, we first need to understand why is heat generation a problem, right? The main concerns with the heat generation in concrete are peak temperature and the temperature differential, right? So when you when the concrete is poured, it's the heat of the hydration process start, and it's an exothermic reaction, which means a lot of heat is evolved. So a lot of standards and specifications, they have a limit on the peak temperature, which is normally from 70 to 75 degrees. So if that somehow, if the concrete is cured at higher temperature than that limit, right, during the, whether it's due to heat curing or whether it's due to heat of hydration, then we have some serious durability concerns, which are mainly due to delayed ettringite formation, right? So with the delayed ettringite formation, what happens that in the later stage during the hardened in the hardened concrete, whenever the thermodynamic reaction conditions become favorable, the expansive reactions take place, and you get like a lot of random macro cracking, right? And the other effect that we get is the strength concern, which means your ultimate strength might get reduced because of this. The other concern is the temperature differential. So when the concrete core is too hot, and the surface temperature at the surface is because the heat is dissipating from the surface, it's cooler than compared to the inner core. So you always get a temperature gradient, right? And whenever this temperature gradient exceeds a certain limit, there is a risk of surface and internal cracking, right? So that is why a heat generation is the main problem for concrete, right? So now we look at the thermal cracking. So thermal cracking can be either due to external restraint, or it can be due to an internal restraint, right? Let's first look at the external restraint, the mechanism behind the external restraint cracking. So we can see here that this is an old concrete, and we are casting a new concrete on the top of that. So it could be a pile cap or a headstock, and this is a small thin wall. So what happens during the heating phase, that it expands, right? The temperature goes up, and as it expands, compressive stresses they develop in the concrete, right? And concrete is strong in compression, so there should be no issue at that stage, and this is the strength development, tensile strength development with age. But in the cooling phase, what happens is that the thermal contraction is occurring, and at the same time we have some shrinkage, which is likely to be autogenous shrinkage at that stage, right? So this is the cooling phase. Now all these thermal contractions and shrinkage are restrained by this old concrete, right? And the degree of restraint will depend on the size of both elements, and the type of concrete that we're using, the elastic moduli. So what happens that it develops the tensile stresses in this concrete, in the new concrete, right? So our compressive stresses, they gradually change to the tensile stresses, right? And as soon as they exceed the limited tensile strength capacity at early age, the cracking occurs. So this is the whole mechanism behind the external restraint cracking. Now in mass concrete elements, the main type of cracking that we observe is due to internal restraint, right? So what is an internal restraint? Now internal restraint is basically is occurring due to temperature differential, as I said, because your inner core is too hot and the heat is dissipating from the surface, so you always get a gradient, right? So no matter if the concrete is insulated, right, you still have a gradient, and also even if you remove the formwork, you will get a much steeper gradient at that time, right? So our temperature differential is basically the maximum temperature minus the minimum temperature at any stage during this process, right? It's not just when the formwork is in place. It can happen once you remove the formwork, so that temperature differential should be at at any stage during this whole process, right? So once now we have we know what is the temperature differential, so we can see how this internal restraint or temperature differential cause the cracking, right? So if you look at this diagram here, in the heating phase, you see the temperature is going up. What happens with the cores, that it expands more than the exterior concrete because it is much hotter, right? So when it expands more than the exterior concrete, the stresses in that core will be compressive stresses at all the time, right? Whereas near the surface you get tensile stresses, and that's why at this stage you have a lot of risk of having surface cracks. Whereas in the cooling stage, what happens that the core, it starts to cool down more rapidly compared to the surface, because surface has already lost a lot of heat, right? So in this case, the tensile stresses then they start to develop inside the core, right? And then you have a risk of internal cracking as well, right? So at this stage, surface cracks may open, and also you can get some internal cracking which may not be visible, from the surface. So this is what happens, with the internal restraint. Now to see the risk of to evaluate the risk of cracking due to internal restraint, we need to calculate the thermal strains, right? So thermal strain is normally calculated as it's just a simple equation. You just multiply the coefficient of thermal expansion of concrete with the temperature differential you're getting. So it depends on two factors. You can see from the equation, so higher the coefficient of thermal expansion and higher the temperature differential, the higher would be the cracking risk. So what we need to do is to eliminate the risk of cracking is to lower these two factors, right? So we need to select the right type of aggregates which have a lower coefficient of thermal expansion, so we can get a lower coefficient of thermal expansion from concrete, right? So this is one way and one thing, and the other thing is we need to control the temperature differentials. Now, how to control the temperature differentials? We can do it in two ways. We can use the insulation or formwork, or we can use cooling tubes, right? So let's have a look at this example on controlling the temperature differential by these two different methods. So this is an example where we have a 1.8 meters deep pile cap, and it is cast using a ternary blend mix S50, and the proposed formwork removal time is 7 days, right? And in first case, we will consider using the formwork or insulation, right? So this is the thermal modeling outcome of this example. We can see the peak temperatures, they're around 70 degrees. The temperature differential within the time where the formworks were in place, they're more or less, near the allowable limit. But as soon as you remove the formwork, there is an abrupt change in the temperature differential. This is called thermal shock. Yeah. So in this particular example, the temperature differential that we are looking at are much higher than the normally allowable limits are like between 20 to 25 degrees. But in this case, we're looking at a temperature differential of 48 degrees, which means there is a serious risk of cracking, right? Now to avoid that, as I said, this first, because we're looking at the first case, we're using formwork and insulation to control this temperature. So we need to extend the period where the formwork or insulation are in place, right? We can extend that period and we can bring that temperature differential down, right, within the allowable limit. In this particular case, we need to keep the formwork and insulation in place for 24 days, right? So if you keep that in place for 24 days, you can get a temperature differential limit within the allowable limit, which is 25 degrees, right? So you can see that this technique takes a much longer time to control the temperature differential within the allowable limits. The much quicker technique is using the cooling tubes. Again, the same example, like but this time we're gonna model it using the cooling pipes, right? So what we are doing, we're introducing 4 cooling pipes, 25 millimeter diameter, with an inlet temperature of 25 degrees, right? So this is the modeling outcome. You can see this is the cooling pipe going through the through the pilot cap. This is the longitudinal section, and you have 4 of these, like running along the width. So what happens then? Now we can see that we have significantly reduced the peak temperature, right? From 70 degrees in the previous example, we have reduced it to 60 degrees, right? Not only that, we have also reduced the temperature differential, right? So this is the formwork insulation removal time, which is 7 days that we considered in the previous example. But this time we're only looking at a temperature differential of 24 degrees, right? And a peak temperature of 60 degrees. So just to make a comparison with the previous example where we have done modeling without any cooling tubes, you can see that the peak temperature, we have not only reduced the peak temperature, but we also have reduced the increased the rate of cooling in the cooling phase, and that's why which is very helpful in keeping the temperature differential within the allowable limits, right? Okay, so next let's move on to thermal modeling. Now thermal modeling is very important, because you need to predict the temperatures, you need to predict peak temperature, you need to predict the temperature differential to assess the risk of cracking, and it is very important to do it accurately, because the errors made at this stage can have significant consequences, right? So the easiest way to do a thermal model is, the first thing to know about the thermal modeling is you need to basically know the adiabatic response of the concrete, right? So adiabatic response can be estimated using Series C766 spreadsheets, right? So Series C7 or Series C7 Series C60 or C766, which is its update. They uses the data which was generated at University of Dundee in 2006, right? So they have a set of data for each supplementary cementitious material and its type of cement. And then you can use that data to basically predict the adiabatic response. This is how a Series C766 spreadsheet looks like. Yeah. So you put your binder content, whatever the binder content you have in your concrete mix. You put the binder type, whether it's a 100% GP cement, whether it has some fly ash in it or it has slag in it. You put that binder type in it, and then you put the addition, like what percentage you're putting in it. And you can easily predict this this graph, right, which is the adiabatic response. But the issue is that it has certain limitations, right? This spreadsheet is based on the experiments which were performed in UK, and and Australian cements are much different from the European cements, and the behavior can be different too, So you can estimate a wrong temperature, and also the other limitation that it has is because you can't use it for a triple blend concrete, right? You can see this option here, the binder type. You can only put one type, like either you can put fly ash in it or you can put slag. But if you have a ternary blend where you have like fly ash and slag together, you cannot use this spreadsheet unless you are very experienced and you know how to handle the situation, and you have the experience of you have seen the adiabatic response of these mixes before. Like you cannot straight away use this spreadsheet, right? So this is the main limitation. So that's why the more accurate way to get the adiabatic response of a concrete mix is to perform a hot box trial, right? So BCRC we developed a two-probe method, which is given in CIA Z70607. So it's a two-probe method. This is how the geometry of of a hot box looks like. It's a 1 cubic meter concrete basically you need to pour. And the data that we get from this hot box test is very accurate. However, it is a semi-adiabatic test, right? You have to keep that in mind. You cannot use that data simply in your modeling because this is a semi-adiabatic test, and you have to change this data to a fully adiabatic, and we can do that at BCRC using our in-house software, which changes the semi-adiabatic data to adiabatic. And then once you get that adiabatic curve, from the graph, you can then generate the heat generating characteristics of the concrete, which then can be used in 2D or 3D modeling to predict the in-situ temperatures, right? Now, in-situ temperatures, again, for in-situ temperatures, there are two different techniques, right? So first one is the simplest one, like using Syria C60 or Syria C766 spreadsheets. Everyone have got access to Syria C766 spreadsheets. It is based on 1D finite difference approximation, mainly used for simple structures, for slabs and walls. And because this method is easy to implement in a spreadsheet, so that's why it's very common, because everyone can use it, right? But it has certain limitations, right? We discussed previously, you cannot use it for triple blend concrete, but apart from that, for in-situ temperature predictions, if you have a complex geometry, like where you have varying thickness, we have varying depth, you cannot predict you cannot use these spreadsheets simply, or even if you have a staged construction where the concrete is poured in lifts, right? For example, in dams, right? So you cannot predict the behavior of lower lift due to the heat generation of the top lift using these spreadsheets. And also, when you're modeling cooling tubes, you cannot use these spreadsheets, right? So you need to these spreadsheets have very basic application. Now, the other method, which is more robust, is you're using the proprietary models, like which can do 1D, 2D, or 3D modeling. You can model any shape, like any geometry. You can model staged construction if you have a wall which is or a dam which is constructed in lifts, and you can model cooling pipes. But for that you need to have a specialist consultant like BCRC, right? So at BCRC we can do all these we have these proprietary models, and we can do all these sort of things. I will give you some examples where we have used these techniques for different projects. So this is a staged construction example where the client has cast this wall, which is a massive wall, like in different lifts. So you can see the thickness of each lift. So this is how we have modeled this this wall, and this is the behavior of each lift, right? So you can see here for example, the behavior of first lift is it has gone to its peak, and then the temperature starts to decrease. And then as soon as you cross the second lift, the temperature, you get another peak, yeah? So you get another peak because of the top lift. This is due to heat of hydration of the top lift. So you cannot model this this response using simple spreadsheets, right? And this is very important in estimating the temperature differential to accurately predict the risk of cracking, right? This is the graph that we have generated using Syria C766, and you can see that you cannot predict that behavior of the first lift when the second lift is cast in here, right? So this is the main difference. Similarly, we have used these models, for complex geometry, like we have used it for a full-scale pier, where to get the peak temperature and accurately predict the temperature differential on each side of the pier. Similarly, this is a complicated bridge segment where you have varying thickness, varying depth. This is a girder with cooling pipes, and then is a complex geometry beam. So you can use these models in different situations. Now the next is monitoring the in-situ temperatures. So in-situ temperature monitoring is very important because it will give you a record of how the concrete is behaving. So you need to have hourly logging of temperatures and daily checking and downloading, which has become very easy nowadays with the technologies like in-situ, with the latest technologies. So you need to have at least two probes in one placement, one at the maximum temperature location and one at the minimum temperature location. When using cooling pipes, the maximum temperature will always occur in the largest area without cooling pipes. You need to install one in that area, in the middle of that area, you know. And also when, you know, when logging is required, where the maturity is used as a means of assessing strength development over time for stripping with no further curing. So with the latest technologies, I was talking about that. For example, this in-situ technology. This is a really amazing technology. I'll talk about some of its key features. That using their in-situ system, the logging probes are turned on automatically, right? So you don't need to wait and look for the concrete to turn it on. You know, a BCRC engineer can install it well before the pour, and as soon as it hits with the concrete, it comes into contact with the concrete, you know, it turns on automatically, you know. So these probes, you know, they also log the data, so you don't need to install a separate data logger. And once your concreting is done, you know, which is a risky process where you can damage your data loggers, you know, and you can attach a single channel, a 4-channel logger to this probe, and you know, then the data can be transmitted directly in the cloud in real time, and BCRC can monitor, you know, and advise the contractor on the outcome, and you know, when to remove the formwork, and you know, when the maturity is achieved, when to strip the formwork. And also, you know, the contractor can get alarms called directly in their email. You know, for example, if you have set a temperature limit of 70 degrees, and if somehow it has exceeded, you know, the contractor will get an alarm clock in their email, right? And same with the maturity. You know, if you have achieved a certain level of maturity, you will get an alarm, you know, notification, and then you can, you know, strip the formwork. So to end with my presentation, I would like to conclude, like, you know, how BCRC can help you in thermal planning. So we can determine the heat output of a concrete mix, whether it is suitable for that particular element size, climate, prevailing conditions. We can modify the concrete mix. We can advise on, you know, appropriate replacement of SCMs. We can alert the contractor or you know, concrete supplier to treat the concrete, you know, as something out of ordinary, you know, if it is required. And also, like, you know, we can inform the ready-mix concrete supplier about the maximum temperature of concrete at the placement for that particular member or for that particular element. Tell the contractor how to keep the temperature differential between the core and the nearest surface, you know, and how to keep that in the specified limit, and how to lower the risk of cracking. Inform the contractor on what to avoid, like, for example, the pour sequencing. You know, we can help the contractor with the pour sequencing, so we should be avoiding any sort of end restraint and, you know, unnecessary restraint that could occur with the poor you know, concrete pour planning. So with that, I conclude my presentation, and thank you so much for your attention.
Okay. Well, thank you, Inam. Very interesting presentation. I'm sure you will all agree. So we have a few questions here from people in the audience. We might just go through a few of those as we have a little bit of time spare before we need to move on to the next talk.
Yeah.
I don't think I will tell people's names who have asked the questions. I'll just read the questions out anonymously.
Yeah.
So, Inam, the first question is, thank you for your presentation. Would the internal cracks normally go unnoticed in practice? And is there the same effect on durability as for external cracks?
Yeah, good question. So yes, the internal cracks most of the time remain unnoticed, and they don't have a lot of consequence on durability unless the element is restrained, right? So if, for example, you have an end restrained element, and if you're getting an internal crack, then that could eventually, you know, come to the surface, and you can see that crack. So you need to avoid internal cracking if it is an end restrained element. But yeah, most of the time they remain unnoticed.
Okay, very good. By the way, everyone, it's Jonathan here. I'm acting as a sort of the MC in terms of the questions here. So another question, Inam, is, in case one example, how do you arrive with the temperature of 70 degrees? Heat of hydration?
Yes, so I've explained that in the in-situ temperature modeling, and you know that whenever you have a concrete mix, you first need to estimate its adiabatic response, you know, and you can do it using if you have your previous library of mixes where you have the adiabatic responses, we have BCRC, we have a library of mixes where we can predict the adiabatic response more accurately compared to Seria C766, which is based on UK. And so once you have the adiabatic response, then you need to model it using your, whether you're using your Seria C766 spreadsheets or you're using your proprietary models. And you have to take into account the formwork, you have to take into account the ambient temperature, the placement temperature, and then it can predict the peak temperature. So that 70-degree temperature is basically come from the modeling. Thank you.
Okay. So another question then, and if anyone has any more questions, there's still time to post on the Q&A function. So please do if you feel so inclined. Another question here, Inam, is does the rate of temperature increase matter in the mass concrete? Sorry, I'm trying to read the way it's written here. Sorry, so I'll start again. Does the rate of temp increase matter in max temperature in the mass concrete? In precast, temperature increases faster than in situ concrete. What happens if the temperature differential is below 20 degrees, but the maximum temperature is, say, 85 degrees?
Yeah, so as I said, with the peak temperature, the main concern you have is the delayed ettringite formation, right? So no matter your temperature differentials are within the allowable limits, so you don't have any risk of internal cracking or surface cracking, but you will have some consequences in the hardened concrete in long term. When you have your temperature exceeds the certain limit, which is allowed from the code, and it depends on your concrete mix design. What you have in your concrete mix design. There is the delayed ettringite formation can happen. In that, so you will have macro cracking. You have expensive reactions later during in the hardened concrete, and you end up having a lot of cracking due to delayed ettringite formation. So you need to control the peak temperature as well, not just the temperature differential.
Yes, okay. I hope that answered the question there from that person. Another question here, Inam, is what about the in-ground structure like piles or diaphragm walls? How do you control the temperature differential while the surface is in contact with water or soil?
Yes, so again, you need to do the modeling, right? So in terms of underground buried structures or structures in water, like for example piles, you have to consider, for example, for the piles in water, you have to consider force conviction, because your concrete is in contact with water. So you have to consider, these what you call it, it's conviction coefficients, appropriate conviction coefficients. To take into account that modeling, and you can still predict, the temperature differentials, and you can still predict the cracking risk, But you need to take into. That's why I said, this the spreadsheets they have limitations. You cannot model this sort of behavior in the spreadsheet. So you need to know. You need to have the knowledge of how you can do the force conviction. How you can incorporate into your modeling. So it comes all from the experience, and then you can do it. Yeah.
Excellent. There's another question here is, have you considered the maturity effects in thermal modeling?
Look, yeah, maturity is it's a separate topic. I haven't touched on it today, but the thing is, maturity normally is related to the compressive strength and not the temperature issue, right? So you are dealing, like, you're looking at a certain compressive strength where you have achieved it, and then you can strip off the formwork once that concrete strength has achieved. But at the same time, if you're looking, for example, if you're achieving the maturity in 2 days' time, right? But when you strip the formwork, you probably expose the structure to a thermal shock, right? And that can create surface cracking. So even though the structure is stable, it will not fall down because you have achieved strength, but you are not following the second condition, which is you have to meet the temperature differential limit, right? So you might end up getting some cracks. So you need to consider both, like maturity and the temperature differential limits, to be able to avoid the surface cracking.
All right, great answer, Inam. And I think it's the final question, although there might be one more after this. It's a short question, so hopefully you can interpret it in them. It just simply says concrete pre-cooling options.
Yes, look, the pre-cooling options are, you can obviously cool down the coarse aggregates or aggregates, like, and that's the most effective way to pre-cool the concrete, because 75 to 80% of concrete consists of aggregates, right? So if you cool down the aggregates, you can bring the placement temperature down, right? The second, you can use the crushed ice, or you can use chilled water, but again, you need to consider the cost of it. If the concrete plant is in a remote area, they barely use the ice, crushed ice in there. But if you are getting concrete somewhere near the city, then they have the facility to batch concrete with the crushed ice, right? And you can also use liquid nitrogen. So these are the pre-cooling options you can do to lower the temperature, which is basically the placement temperature.
Fantastic. Okay, a final question then before we move on to the next talk on creating durable basements. How is the in-situ monitoring priced? Is there an indicative rate in terms of dollars per metre cubed of concrete, for example, where a job has in excess of 1,000 metres cubed of concrete, or is it strictly project specific?
Yeah, look, it's a bit hard to answer the question. It depends on several factors. Like, as I said, you need to have at least 2 probes per placement. And depends on how many elements do you have. Like, for example, if you have, it depends on the concrete quantity, but it also depends on the number of elements you got, right? So for each element, each mass element, you need to have at least 2 probes, right? But if you have a raft, for example, and it has the same thickness throughout, you may not require that many probes, right? But whereas if you have a bridge where you have, a lot of head stalks, a lot of mass concrete elements, you need to have those probes in each of the element. So it's really difficult to answer this question, and it varies from project to project, and then also sometimes you have these in the specifications from the client, and yeah, so this is pretty much it.
Okay, a tough one to finish on.
Yeah.
All right, so I hope everyone enjoyed our first talk there on thermal and early age crack modelling of large concrete elements. Thank you, Inam.